Welcome back. To build a triangle, can you use any 3 side lengths, or are some combinations physically impossible? Let's test this with a real-world layout. Imagine you are standing at the entrance of a campsite tent, and you want to walk to that palm tree over there. You have 2 options. Path 1, walk straight across the grass directly to the tree. Path 2, walk up to the wooden pole first, then turn and walk to the tree. Which path is shorter? It's the direct route. A straight line between 2 points will always cover less distance than a roundabout detour through a third point. This intuitive rule is known as the Triangle Inequality Theorem. This walking logic establishes the physical requirement for 3 segments to meet and form a closed shape. Let's apply our path logic to a test case. Can a triangle with side lengths of 10, 15, and 30 centimeters actually exist? For it to work, every single direct path must be shorter than the detour through the third corner. If we take the 10 centimeter side as our direct path, the detour is 15 plus 30, or 45. 10 is less than 45, so that works. If our direct path is 15, the detour is 30 plus 10, or 40. 15 is less than 40. That works too. But look what happens when we make the 30 centimeter side our direct path. The detour is 10 plus 15, which is 25. The direct path of 30 is longer than the 25 centimeter detour. Because a direct path cannot be longer than its detour, this triangle is impossible. The standard textbook method asks you to test all 3 of these algebraic equations for every problem. That takes time and requires 3 separate calculations. Here is the shortcut. Identify the longest side. Then check if the sum of the 2 smallest sides is strictly greater than that longest side. Pause the video here and use this shortcut to evaluate these 3 sets of side lengths. Which of these can form a triangle? Let's check them. 3 plus 4 is 7, which is less than 8. 2 plus 3 is 5, which is less than 6. The first 2 combinations fail, but in the third combination, 4 plus 5 is 9. Since 9 is greater than 8, this set of numbers works. To see exactly why this shortcut works visually, let's look at this digital radar grid showing a baseline equal to our longest side of 8 centimeters. If you attach the 2 smaller sides to each end of this baseline and swing them like compass arcs, they act as expanding circular radii. In 2-dimensional space, this creates exactly 3 possible geometric scenarios. In the first scenario, where the sum of the smaller sides is less than the base, the circles stop short. They leave a gap, showing that the sides cannot reach each other to form a third vertex. In the second scenario, where the sum equals the base, the circles meet at a single microscopic point, resting directly on the baseline. They don't form a triangle, just a flat line segment. In the third scenario, the sum is strictly greater than the base. The circles overlap and collide at a point above the line and a second point below it. Connecting the ends of our baseline to either of these collision points successfully creates a closed triangle. These mathematical inequalities are literal reflections of how physical circle boundaries must behave to close a shape in 2-dimensional space. Now it's your turn. You have a triangle with 2 known sides, 5 centimeters and 10 centimeters. What is the range of possible lengths for the missing third side? Remember, it must fall strictly between the difference of the known sides and their sum. Calculate the mathematical limits using that formula, pick the minimum and maximum whole numbers that fit, and drop your answer in the comments below. Before you go, here's a summary of today's shortcut rules. Take a screenshot and remember to like this video and subscribe to Textbook Toonz. Next time, we move into SAS, ASA, and Euclid's 180-degree rule. These proofs rely on the boundary logic we established today. See you then!